Hi, I'm Adyasha Mohanty, a graduate student in the NAV lab at Stanford University, and I'll be presenting a particle filtering framework for integrity risk of GNSS-camera sensor fusion. The objective of this work is to jointly estimate the state and calculate integrity risk for GNSS-camera fusion. We develop a particle filtering framework where we first derive a probability distribution over position from camera images, and secondly, design a metric to fuse probability distributions over position from both GNSS and camera while accounting for multiple faults. As illustrated in this picture, the particle weights in this filter are derived jointly by assessing the consistency of GNSS and camera measurements, which ultimately form the distribution over position. Intuitively, increasing weight represents more correct measurements, while decreasing weight represents a faulty measurement. Our first contribution is deriving a probability distribution over position using map matching. We designed a three-step approach for this. In step 1, we create a database of images which are selected from a geographical region with known coordinates. Then we extract features from this database of images as well as images that we receive at runtime. In the second step, we utilize a concept from computer vision known as vocabulary tree, which helps us to compute similarity scores in a computationally scalable manner. These scores represent the degree of similarity of each test image with respect to images in the database. Based on these scores, we can find the best matched image and its corresponding coordinates. In the last step, we compute a probability distribution over position by passing these similarity scores through a softmax function. Our second contribution is formulating a KL divergence metric to fuse GNSS-camera probability distributions. The first step is forming a unimodal likelihood from each camera image using map matching, as shown previously in slide 2. The likelihood from successive images is then propagated to a unified timestamp utilizing IMU motion data. In the second step, we formulate a Gaussian mixture model or GMM utilizing GNSS pseudo-range measurements. This approach is directly used based on our prior work published at ION GNSS 2019. Then we formulate a KL divergence metric inspired from information theory, which essentially assesses the consistency of position distributions from GNSS and camera. Specifically, we minimize the divergence of each distribution from camera with respect to GNSS to compute camera weights. These weights are then incorporated as different components in a mixture of experts model, which characterizes the distribution over position from all possible camera images. Finally, assuming conditional independence, we derive the final position distribution. We then perturb this distribution using IMU motion data to derive the integrity risk for a given alert limit. Thank you.